Welcome friends to this second lecture of week 6 or module 6. In this week we are talking about kinetics of soil chemical process. So, basically in this week we are supposed to cover these topics. So, in the first lecture we have covered these rate limiting steps and time scales of soil chemical process, and then we have also discussed about the chemical reactions and the rate laws. Now, so today we are going to focus on the determination of different reaction orders and rate in this lecture. So, before going to that, I just want to give a quick recap of whatever we have discussed in the last class, so that it will be helpful for you to relate whatever we are going to talk about in this lecture. So, let us go ahead and see. We have in our first lecture we have first discussed why study the soil chemical kinetics. Now, soil chemical kinetics is very important because soil chemical processes are very time dependent, and different metals, oxyanions, radionuclides, pesticide, industrial chemicals and plant nutrients, and their reaction is governed by these different chemical kinetics. So, that is why it is very important that we should learn about the chemical kinetics, and we also need to predict these fates of these different metals, oxyanions and radionuclides, pesticides in the environment. So, for that also we need to understand what is the what are the soil chemical kinetics. And then we have talked about these 6 different rate limiting steps or transport process. The first process, as you know, it is the transport in the solution phase, as you can see, and which is basically very rapid, because in the laboratory we can facilitate this by rapid mixing. The second step was transport across this particle liquid interface, and the third phase we have talked about the transport within these liquid filled macropores, the macropores which are having the diameter of greater than 2 nanometers. So, the fourth one which we have talked about is basically the diffusion of sorbate along the pore wall surfaces, which is called the surface diffusion, as you can see here. The fifth one we talked about the diffusion of sorbate occluded in micropores, which is denoted by this in this 5, and the sixth one we have talked about the diffusion of the bulk of the solid. So, this is the sixth one. So, apart from this, so this diffusion from the bulk of the solid is basically a activated diffusion process. However, the movement through the macropores and the transport to this diffusion of the sorbate at the surface of the solid is non active diffusion, examples of non-active diffusions. There are different rate limiting steps, as you can see here. There different types of soil chemical process are depend on time. So, for example, ionization, ion exchange, as you can see here, are very short period. They are very they are present for a very short period, or these reaction occurs in very short period of time, varying from microseconds to minutes, and just opposite to mineral crystallization, which can takes years to millennium to occur. Now, these reactions can also occur simultaneously and consecutively also. Now, we know that variation on the different types of soil clay colloids also shows different types of reaction rate. For example, kaolinite and smectite can produce higher reaction rate than that of vermiculitic and micaceous soil. The reason is, in case of kaolinite the external surface area is more, however, in case of smectite, for example, Montmorillon, the internal surface area is high. So, these surface areas are available for reactions. So, as a result, the sorption mechanisms occur very rapid in these surfaces, and they basically take seconds to milliseconds to occur. Now, in contrast, in case of vermiculite and mica, you can see that they have multiple sites for retention of metals and organics, including the planar edge and collapsed interlayer sites, because due to the presence of this potassium ion in the interlayer site, their interlayer space is collapsed, and as a result sorption and desorption mechanisms on this site can be very slow and very tortuous. So, these reactions, sorption can involve either 3 reactions. One is high rates of of reaction in the external site, intermediate in the edge, and low rate in the interlayer sites. So, we also talked about chemical kinetics, definition of the chemical kinetics. Now, it is the investigation of the chemical reaction rates and the molecular processes by which their reaction occur where transport is not limiting, where in contrast kinetics is basically the study of time dependent process. Now, it is difficult for determining the chemical kinetics for a homogeneous system, and the things become more complicated when you talk about soil which is highly heterogeneous system. Now, that is why it is extremely difficult to eliminate the transport process in soil, because that is a mixture of heterogeneous mixture of inorganic and organic processes and adsorbents. So, we also talked about the rate loss and implication of the rate loss. Now, remember that rate loss helps us to determine how rapidly reaction attain the equilibrium, and secondly it helps us to infer the information on the reaction mechanisms. Different types of rate loss, I have showed you these elementary equations, elementary reactions, and here A, B, Y and Z are stoichiometric coefficients, and then we have defined different types of constant based on that. So, based on these rate laws, we have seen that the rate of reactant A above, which has a concentration which is given by this bracket at any time t, can be denoted by these by this rate. However, while the rate of regard to product y having a concentration of this bracketed y at the time t can be defined by this dy by dt, and the rate expression here can be defined as dy by dt equal to minus dA by dt. Now, dA has we are putting a minus sign because as the time progresses there is a continuous decrease in A concentration. So, which can be expressed in terms of this constant multiplied by A alpha and B to the power alpha, whereas this K is a it is a rate constant, alpha is a partial order for reactant A, whereas the beta is the partial order for reactant B, and these orders are experimentally determined and not necessarily their integral numbers. We will see these in details in today's lecture. Now, remember this, the sum of these partial orders are always equal to the overall order of n. Once the values of alpha, beta and determined experimentally, that rate law is defined, and reaction order provides the information about the manner in which the rate depends on the concentration. We will see that today in today's lectures. So, order does not mean the same as the molecularity, remember, which concerns the number of reactant particles entering into the elementary reactions. Then we have talked about different types of rate laws. We have talked about these 4 different types of rate laws. One is the mechanistic rate laws, then apparent rate law, then transport with apparent, and then transport with mechanistic. In case of mechanistic rate law, it assumes not only the chemical kinetics are operational and transport phenomena, and where the transport phenomena is not occurring. So, it basically nullifies the transport phenomena. So, it is difficult to determine the mechanistic rate law in most soil chemical system due to the heterogeneity of the system caused by different particle size, porosities and type of retention sites. The second type of law is apparent rate law, where both they consider both kinetics and transport control processes. So, the third one which you have talked about is transport with apparent rate laws, which emphasizes transport phenomena and assumes first or zero order reaction. What is first order reaction, what is zero order reaction, we will learn today. And the fourth one is transport with mechanistic rate laws, that is which can be described simultaneously transport control and chemical kinetics phenomena. It basically encompasses both chemistry and physics, physics from the chemistry and physics based explanation of the total chemical system. So, today we are going to start with this definition as well as the concept of these different order reactions. So, first we have to learn what is the first order reaction and second order reaction. Now, in the first order reaction, the reaction rate depends on the concentration of one of the reactant. However, in case of second order reaction, the rate is proportional to the square of the concentration of a reactant or the product, or product of the concentration of the two reactants. So, While in the first order reaction, the rate of reaction is basically depends on the concentration of one of the reactants. So, we can consider only one of the reactant. However, in case of second order reaction, the rate is proportional to the square of the concentration of a particular reactant or the product of the concentration of the two reactants. So, we can view it from either aspect, either from a point of view of a square of the concentration of a particular reactant, or it is a product of concentration of the two reactants. We will see that in details while we are going to discuss different differential form as well as integral form of these equations. So, what is the first order and second order reaction? Now, remember, we can express this first order reaction, second order reaction. So, before going to that the actual soil related first order and second order reactions, I want to discuss the concept of first order and second order reaction, as well as we will be talking about zeroth order reaction, and then we will be seeing how these type order reactions, so first order, second order and zero order reactions are actually been implemented in soil chemical processes. So, let us first clear our concept of different orders of reaction. So, if you see, the differential rate laws are generally used to describe what is occurring in a molecular level during a reaction, whereas integrated rate laws are used to determine the reaction order and the value of the rate constant from experimental measurement. Now, remember, any type of reaction order, for example, first order reactions or second order reaction or zero order reaction, can be expressed from both differential point of view as well as an integrated form. Now, in case of differential form, it basically describe what is actually going on in the molecular level during a reaction, whereas in case of integral form, which we will see right now, are used to determine the reaction order and the value of the rate constant. So, the differential equation describing the first order kinetics can be given as such. For example, here rate is equal to minus dA by dt, as you know, that is the negative sign is given because the rate is decreasing. Here is can be expressed in terms of K multiplied by concentration of A or Ka. So, basically here the partial order here for A is 1. So, the reactant partial order is 1. So, the rate is the reaction time here. Basically this rate is basically the reaction time, and it can be expressed as unit of molar per time, and K is basically the reaction rate coefficient, which is denoted in the unit of time inverse. So, it could be either second inverse or minute inverse. We will see that in a while. So, however, the units of Ka vary for non first order reaction. We will see that while we discuss the zero order as well as second order reactions. So, this is the basically differential equation describing the first order reaction, where the rate of decay of A is basically proportional to its concentration, and here the constant is known as the reaction rate coefficient. So, these differential equations are separable, which simplifies the solution as demonstrated below. So, as you can see here, first we can write the differential form of the rate law. As you can see here, rate in terms of minus dA by dt, which is basically K multiplied by concentration of A. Now, if we rearrange this, we will get this dA by A we will get minus K dt. So, this is the rearrange, after rearrangement we can get this form. Now, we know the according to the rule of integration rule. So, if we can integrate both sides of the equation. So, now we are getting dA by A equal to minus K dt. So, if we integrate from A0 to A, and in this from T0 to T for any specific time duration, we will have this type of expression. So, basically we will get 1 by concentration of A into dA equal to minus T0 to T integrate K dt. So, this form we will get by integrating in on the both sides of the equation, differential equation. So, now we know that from the integration rules, we know that if we do integration of 1 by x, that becomes log of x, natural logarithm of x. So, upon integration we will get, so basically in the previous if you remember the previous equation which we just saw in our last slide. So, this is basically this integral equation, this integration equation. So, if we consider this integration equation and convert it to the logarithmic form, we will get this equation where log of A concentration A minus log of concentration A 0, that means at time 0, that means at the initial point from where the reaction starts, we will get a that will be equal to minus k T, because we are integrating from time 0 to time t. Now, if we rearrange this equation to solve for this concentration of A, then we will obtain one form of the rate law like this. So, log of A equal to log of A 0 minus k T. Now, you see this can be further rearranged to log of A equal to minus k T plus log of A log of concentration of A at time t 0. So, this is basically a rearrangement of this form, which is further a rearrangement of this form. So, if we can consider this equation that, so if we consider this equation can be arranged in the form of y equal to mx plus b. Now, you know this y equal to mx plus b is nothing but the equation of a straight line. Okay. So, here you can see it is basically taking the form of y equal to, it is mx plus b. So, basically we are getting y equal to mx plus b, where mx equal to minus k T and minus k T, whereas b is equal to logarithm of A. So, from here we can see one thing, that here the slope m is basically this if we consider this m as slope, then mx is basically minus k T as we have seen, and the y intercept b is basically log of A 0. Okay. So, the summarily this equation can be represented in the form of a straight line. Now, once we can describe this equation in the form of a straight line, now recall from the rate laws of recall from the logarithmic laws, that if we logarithm of A t by A 0 equal to minus k T. So, basically we know here is logarithm of A t, it was our equation, minus k T plus ln of A 0. So, if we simplify that, we will get this logarithmic form. Here A is the concentration at time t and A 0 is the concentration at time 0 and k is the first order rate constant. So, this equation which I present here in the logarithmic form is basically, if we go back, this is basically the simplified form or rearrangement of this equation, which is basically arranged in the form of a straight line. So, once you get this logarithmic form, now if we plot it, if we plot this whole the form of if you plot the time versus logarithm of at, then here the intercept will get a0, and here you can see we will get this straight decay line. So, these are basically called decay profiles for first order reactions. Now, here you can see there are two different constant. One is in one reaction you are getting smaller k, another reaction you are getting larger k. In case of small k, when the rate constant is small, then the rate of decay is relatively less. However, when there is a large k, the rate of decay is quite high. So, there is a steep slope in case of large k. So, this is basically the decay profile. So, basically if you plot the time versus logarithmic of concentration at any particular time, then you will get a negative slope as well as a straight line. So, this is the most important feature of a first order kinetics. So, in any type of reaction, if we just plot the reaction time versus the concentration at a particular time, and graphically you want to see what and if you get a straight line with a negative slope, then you can be confident then that it is basically following a first order reaction. Okay. Now, so because the logarithm of numbers do not have any unit, the product of minus kt also lacks unit. Since it is the logarithmic, we have also already seen this kt is nothing but the log of at by a0 equal to minus kt, we already know. Now, for logarithmic of any number basically do not have any unit. So, this kt also do not have any unit. So, if this kt is unitless, that means the unit of k should be always time inverse, because if the unit of k is time inverse, then this time unit and this time inverse unit will basically nullify each other to get a unitless number. So, examples of time inverse is basically second inverse of second or inverse of minute. Thus, the equation of a straight line is applicable here. You can see here this is what we have discussed in previous two slides. So, the straight line and negative slope is the major identifier of the first order reaction. Okay. So, so to test if it is a first order reaction, you have to basically plot the natural logarithm of a reactant concentration versus time and see whether the graph is linear. If the graph is linear and has a negative slope, then the reaction must be a first order reaction. Now, to create another form of this first order rate law, if we take exponential in this previous equation. So, we know that in the previous equation it is basically log of a equal to log of a0 minus kt. So, if you take an exponential in both sides of the equation, then we can get it more simplified form. So, this is concentration of a equal to concentration of a0 multiply e to the power minus kt. So, this is basically the second form of the rate law, where it is following a first order reaction. Okay. So, here it is given here. So, this is concentration of A equal to can be expressed in terms of this A0 e to the power minus kt. So, now the integrated forms of the rate law can be used to find a population of the population of the reactant at any time after start of the reaction. Now, plotting the logarithmic of A concentration with respect to time for a first order reaction always gives a straight line with the slope of the line equal to minus k. We know that. Sometime in some literature you will say that minus k by 2.303. Why it is k by 2.303, we will see that later. But remember that still the value of k by 2.303 is a constant. So, it does not matter, we can use a minus k as a constant. So, this general relationship in which the quantity changes, that means concentration of a particular reactant changes at a rate that depends on its instantaneous value, is said to follow an exponential law. So, basically there is this decay, as we can see in the previous decay profile, it is basically following a an exponential decay. So, exponential relationship are widespread in science and in many other fields. Remember, consumption of a chemical reactant or the decay of a radioactive isotope, all of these follow exponential decay, and its inverse, the law of exponential growth, describes the manner in which the money in a continuous compounding bank account grows with time, or the population of any colony reproducing organisms like bacteria. So, bacteria follows a exponential growth. So, the reason that the exponential growth of a colony reproducing the reason that the exponential function, that is y equal to E x, is so efficiently describes such changes is that if you take a if you differentiate the e to the power x in terms of dy by dx, we will get the output as E x. So, it is E x is basically its own derivative. So, derivative of E x equals to E x. So, that makes the rate change of y identical to its value at any point. So, that is why these exponential decay shows the best representation of first order differential equation. Okay. Now, if you consider why it is called a exponential decay, basically if you put the time versus concentration, you will see there it is following a exponential decay. Now, so that is basically log normal. So, whenever you convert it to logarithmic form, you will get a straight line. So, the following graph represents the concentration of a reactant versus time for a first order reaction. So, this is basically the identification mark of a first order reaction. It will show you, if you basically plot the time versus concentration, you will see an exponential function, and if you take a logarithm of that concentration, you will see a straight line, and the straight line have a negative slope. So, this is the graphical representation of first order reaction. Okay. So, so if we graph, just for an example here, it is a good example is given. So, if you plot the logarithm of a concentration of a reactant with respect to the time for a first order reaction, it basically gives a straight line. So, basically here you can see is the time varies from 0, 1, 2, 3, 4, 5, and you can see first order, in case of first order reaction, the concentration changes from 40 unit to 35 to 30, 25, 20 and 15. So, if you plot that, you will get a basically straight line. So, so basically if you it again says that how this empirically this first order reaction can be identified by just plotting them, the concentration or logarithm of concentration versus time. So, guys, I hope that you have learned something new, at least for first order reaction you have learned today, and in the next lecture we will be talking about the second order reaction, zero order reaction, and and how to calculate the half life of the first order reaction, and what are the other kinetics model applicable in soil science. So, let us wrap up this lecture, and the next lecture we will be talking more about these second order reactions as well as the other types of kinetics models. Thank you very much.